All right, on to part 4. Why is this important? And some of the properties of the normal distribution is what we'll cover in this short section. So why should you care? Many distributions that we'll see comprise a normal distribution. It's natural. It's a product of nature. This isn't some stuff that statisticians built up. Humboldt State students are supposed to love nature, so you should love the normal distribution. That never works live, probably didn't work for you right there. Whoops. Another issue is that a lot of analyses assume some properties that are related to the normal distribution. A lot of the analyses that we are going to engage in assume that we're talking about variables that are roughly normally distributed. When we move on to things such as the t-test, ANOVA, correlation, regression, these are kind of like the heart of this class, the really usable stuff, the sort of stuff that drives the analyses that you see in research papers. All of those make some assumptions about our variables and whether they're distributed normally or not, or how they're distributed. So a lot of stuff rests on the assumption that we've got some normality, we've got some aspects of normality in our data. If we don't, it's problematic, and we can't really use some of the statistics that we want. Where we'll eventually go with this, and keep in mind that this section is this entire section on normal distribution is kind of like building block stuff, not really stuff that you see applied directly. Where we're going to end up going with this is that normal distributions are going to allow us eventually to draw inferences regarding likely values of a variable. For example, what percentage of scores would we likely see between 2 points? How likely would a specific outcome like getting an A be? These can be either exact or approximate depending upon how normal the shape of our distribution is. If we do follow a normal distribution, they'll be extremely accurate. But again, we are making approximations. And then the real important part, which we'll get to in another section later in the class, is that when we're talking about samples that are drawn from a distribution, those distributions, or the distribution of means that would come from samples, reflect the normal shape. And that allows us to draw inferences based on those samples. It allows us to do all of these things that we'll see are going to be central to statistical inference. We'll talk about this more when we talk about the sampling distribution of the mean. And we've got a guest again. We'll talk about this more when we get to the sampling distribution of the mean. But again, a lot of this is going to be really central to kind of the meat of this course, which is statistical inference later in the semester. A few properties of the normal distribution that you should know. The mean of a normal distribution is z of 0. It's always z of 0. And that's, if you think about the formula where you've got, if you think about the z-score formula, that should make some sense, and we'll take a look at that in a sec. Half of the scores are going to fall at the mean or above, and half of them are going to fall at the mean or below. So we're going to have half on one side, half on the other. We usually express values as proportions. For example, we might talk about 0.5 at or above the mean. We can talk about ranges of scores. There's some phrases that we'll use: equal to or greater than, equal to or less than, more extreme than, a variety of different phrases we'll use. And what we'll see is that this really links up very nicely to what we cover in the next section briefly, which is probability. So proportions are actually probabilities. We could ask questions like, how likely is it for somebody to get an A in this class? Well, it happened about 0.07. The proportion there, or the probability, is 0.07. So about 7% of the time, a person would get an A. All right, some terminology regarding areas. Greater than or equal to, scores that are higher than, at or above a certain value. Less than or equal to, scores that are less than or at a certain value. More extreme than is probably the one that most people have challenges with. This means scores that are more extreme in either direction. So if we were talking about a z of 1.0, it would be on either side of 1.0. Above 1, more negative than -1. So why is the mean always 0? Well, if you look at the z-score formula, whatever score is at the mean is going to have a 0 in the numerator. So the mean would be right there, right down the middle. Why do we have 50% at or above the mean? Well, here's at the mean, and there's the values above the mean. You can see that that's half of the distribution. Similarly, at or below the mean would just be the other side. So consider the entire area 100%, that's half of it. All right, and a few other phrases, greater than or equal to a z of 1.0, that's reflected in the red area to the right here. Less than or equal to a z of 1.0, that would be the area to the left of that line. That's reflected in the blue. At or below z of 1.0, we might say this that way. And then more extreme than 1.0. More extreme than a z of 1.0 means bigger than 1 or more negative than -1. So scores in either direction. Oftentimes we look at distributions in this manner. This is what's commonly called looking at two tails of the distribution. And that's a very common thing that we'll see. We often use both of the tails and ask about how likely it is to get a score that's that extreme. So oftentimes we want to know what a z-value is that captures a specific proportion in the middle of our distribution. For example, what z-value captures the middle 90%? Here we wouldn't actually need any calculations. We could just go to our z-table and say, okay, well, where do we have a value of 0.05 above our z? It'll be the same on either side, and that's going to be about 1.64 if we were to look that up. And you can see graphically it corresponds to roughly that.